Okay, let's go ahead and get started today. We're going to go through something that should be useful for your game no matter what your game is, and that's this kind of optimization method using a special module called Numba. And what Numba is, it's kind of a just-in-time compiler for Python code that can automatically take your Python code, which normally runs on an interpreter, and it can convert it into machine code that's compiled. And what just-in-time means, as far as a just-in-time compiler, it means that rather than having to run it through a compiling process, when you run the code, it compiles it as it needs to. So it'll compile certain functions that we tell it to, certain parts of the code that we tell it to, as we need it. But what that does is it allows your Python program to run at speeds well beyond what the Python interpreter could run them at. And then the problem that we're going to look at doing that with is kind of this simulating an infectious kind of transmission process, which is a fairly timely thing to look at the way things are right now. All right, so let's go and get started on that. So simulating that infectious process, let's talk about that first, and we'll get to the Numba stuff a little bit later when we need to optimize it. But what we're going to do is we'll spend a very little time going over this, and here we'll go over it in the code primarily. But essentially what we want to do here is we want to kind of simulate people. So we're going to have this concept of people that we're simulating, and those people objects, we're going to allow them to kind of move around. So they're allowed to kind of wander around in their world. And here's how it's going to work as they move around. So the people will move about, and we're going to select one or maybe a few of them that we say these are going to be our initial kind of infected individuals. And then if those people get too close to some other infected person, then what we're going to do there is, let me turn down the gain on the mic just a little bit. What we're going to do there is if they get too close, they'll infect somebody that they've come in contact with or come near. And then once somebody's infected, they're going to remain infected for a period of time. And at the end of that period of time, which we're going to specify, there are two outcomes. Either they become healed, and then therefore they are now immune or resistant, or they're going to die. And so that's essentially the model. People walk around. Some of them are infected, some are not. If an infected person comes in contact with one who's not, the infection gets transmitted. Once people are infected, they remain infected for a period of time, and then they will either get better or they won't. But we're going to kind of simulate all this. Now, to simulate that, we're going to run some simulations where we allow the people to kind of wander very broadly, and we're going to then kind of restrict their motion with kind of this kind of idea of social distancing that we see right now. And then we're going to look at how that plays out with the things. And we're actually going to visualize that. We'll use pygame to visualize that. And then after we get it up and working, we're going to say, well, notice one of the things is it's going to be fairly slow. So we're going to kind of speed that up, or work on speeding that up with that Numba module. Now, we can't really just throw Numba at the entire project, or we're not going to right now. We're going to throw it at just the parts that are the slowest. And there's a particular kind of thing called Amdahl's law that basically says we should spend the most time optimizing the part that's the bottleneck. It doesn't do much good to optimize the parts of the code that are not really contributing to the slowdown. So we're going to focus our efforts on the part of this that is the bottleneck. And that's the part where we're checking to see which person is infecting which other person as they get near. All right, so let's go ahead and write some code. And seriously, I'm going to switch over to Python. We're going to write some code here. So let me bring up a Python shell, Python interpreter here. And let me move this over here. And let me switch so you can actually see the window. Okay, so here's our Python, a brand new blank slate. Let me change the font so it's a little bit bigger so it's easier for you to see. Okay, so now I've got this window up. let's go and get started kind of writing some code here. So the first thing that I'm going to start with in the code that I'm going to put in this window is, and let me move this over to the side a little bit here. Let me make the code window a little bit wider. All right, so the first thing is I'm going to put a comment here. We're just going to give this a name. And I apologize about all the noise outside. There seems to be a storm going on and some sort of a emergency response vehicle driving around. Now, so to start off with here, we know we're going to use pygame. So let's go and import that. We know we're also going to have to do some math in here, so I'm going to import math. There are a couple other things that I probably want to make sure that I have access to. We're going to probably need some randomness. Import random. And eventually we're going to need Numba, but I'm not going to add that right now. All right, so to start with, the first thing that I'm going to do is I'm going to have the screen be some certain size. It's going to be kind of like our world has some fixed size. We're just going to use a rectangular screen. So we're not going to make a globe or anything 3D, anything like that. We're just going to use a screen. So it's going to have a width and a height. So I'm going to go and define those. So screen width. And notice I'm using these all caps constants here for these things. The reason that I'm doing that is so I can see those in the code, that those are kind of the levers I'm going to pull, or the things I can change that are constants later on. So I'm going to start off with, let's see, I have a fairly large screen here. So I'm going to make this, like, let's make that 1800. And let's make the screen height, well, let's make it half of that. So let's make it 900. All right, now, before I do anything else, I'm going to add some other things. So I want this thing to run at a certain set frame rate. So I'm going to go ahead and define a frame rate. And the frame rate I'm going to define this as is, we don't need this to be super high fidelity. We just need to see what's going on. So I'll define the frame rate at 30. So something relatively low for a game. All right, now we're going to come back and add some other things later on. But let's go ahead and get the main part of the game loop up and running. So with the game loop itself, I'm going to have to initialize pygame. So I need to do that. The other thing that I'm going to need to do is I'm going to need to actually create a display surface. So display surface equal pygame dot display dot set mode, and we want that to be the size that we specified up here. So screen width, screen height. So now we have our display surface. So the display surface, remember, is just the window. It's like a surface, a rectangle that we're going to write the pixels to when we actually draw things. All right, so we've got our display surface created. And now I'm going to go ahead and make a game loop here. We're going to add some stuff before this in a little bit. But right now, let's just get the game loop up and working, make sure that works, and then we'll come back and add some things later. So the first thing I'm going to probably want to do in the game loop is I want to pin my frame rate at that frame rate there. So in order to do that, I'm going to need to make a clock object. So I'll say FPS clock equal pygame.time.clock, and that's a clock object, so capital C. And then at the top of the loop here, I'm going to say FPS clock dot tick, and I'm going to tick it at my frame rate. All right. Now the next thing I'm going to do is I want to get keyboard input to be able to exit this loop with escape, and eventually I'm going to add some other keyboard options to do some things as well. So I'm going to go ahead and get the key state. So keys equal pygame.key.get pressed. So that's getting the state of all of the keys on the keyboard, which ones are pressed and which ones are not. And one of the things, in order to use this, I need to make sure I handle any events that are coming into my window. So pygame.event.pump, I'll do that before I get the key state. And then in the key state, I'm going to say if keys, so if in that keys array, we'll make it so if they press the escape key, so if pygame.k_escape, that's the escape key, if that's pressed, then we'll do a break to get out of this loop. Now the other thing we're going to probably want to do in our loop is we're probably going to want to at some point clear the screen. So ds.fill. fill it with black. We're going to eventually render some stuff, but we're going to want to update the display. So pygame.display.update. So we'll update the display. And then after the loop has ended, once we've escaped out of this or quit the program in some way, pygame.display.quit. All right, so now we have a skeleton of our program here. What I would usually do when I write this is I'll run this. Give it a name. And I'll run the program. And there you see it. You can see it running. And nothing shows up on the screen, but it is running. I hit escape. It goes away. Okay, so now that we got that working, and I'm going to move this shell window over here so we can see that if we ever need to print anything out later. So I'll put that there for now. That'll be behind here. All right, so the next thing that I want to do is start to add some of those features in there to make this thing do the population simulation. So kind of a core part of that is going to be this people class. So I'll say class, and let me call it person. All right, so this is going to have a constructor, so def. And I'm not really going to pass anything into this constructor because I'm going to just kind of make the people randomly. You could make it so you can set a person wherever you want. You could give them different characteristics. I'm going to kind of give all the people kind of a random set of characteristics. So one of the things they're going to need, we're going to need to have, I guess one of the things that would make sense to have here is going to be, each of them is going to have an x position. So self.x equal. And where are we going to put that? I'm just going to pick a random integer somewhere between 0 and this is the x. This is going to be screen width. And screen width is the number of pixels, but since it starts at 0, we're going to want to do -1 here. All right, so there's the x. We're also going to want to give them a random position in y. So we'll say self.y. And this is going to be the same thing, but screen height. Now, let's go ahead and give them, as they wander around, we want them to wander on the board, so they're going to have to go at some speed and some angle as they move around. So I'm going to go ahead and give them that. So I'm going to say self.angle equal. And let's go 0 to 360. And let's give them a speed, so self.speed. And for the speed, I think that I'll give, I don't want that to be whole numbers or integers like with the angle. We could make the angle not be whole numbers as well, but I'm going to want that to be kind of more finely grained. So I'm going to say their speed is going to be random.uniform, which gives a floating point number. I don't want to put that to 0 because I don't want to have anybody stop. So I'm going to have 1, and let's go up to a speed of 5. And that speed of 5 there, that's just going to be in pixels for each frame of motion. So that's the fastest they can be. The slowest they can be is 1. And uniform just means there's a random number uniformly distributed in there somewhere. So the slowest people will move around at 1. The fastest people will move around at 5. Now, a couple other things. Since we're going to be tracking the lives of these things, I'm going to start off the people all as being alive. I also need to track whether or not they've been infected or not. And they're going to start off as not infected. And then I also want to track which ones of them have been infected in the past and have then been subsequently healed. So I'll say healed. They're all going to start off as everybody's alive, nobody's infected, nobody's been healed yet. Now, there are a couple other things that I want to add to this before we move on too much further. And one of them is I want to have this, once they're infected, we need to know how long before they become healed or before they die. How long does the infection last? So I'm going to do self.infection timer. And I'm going to start that at 0 because until they get infected, we're not going to set the timer to anything. In other words, once they get infected, the timer starts. We're going to count that timer until it gets to the point where they either die or they get healed. Last couple things that we want to add here is we want to set some, since we're going to do social distancing and add that later on, I probably want to have some way of knowing how far they've wandered from their home position or where they started. So I'm going to do self.home x And let me do home underscore x. I think that looks a little cleaner. And I'm going to start that at just wherever they start on the screen is their home. So we have that for x. Let's copy paste this. They have a home for their y. And we also want to be able to change how far they can wander from a home. So I'm going to call this like the roam limit. And for right now, I'm going to set this equal to, well, I could set it to a number, but let's do what we did with those constants up there. Let's make a variable for that. So we're going to be able to easily change that right up here and dealing with that. So here, roam limit equal. And let's start it off with something somewhat high. Let's start it off at like they can wander 500 pixels from their home. So that's a relatively high roam limit. We're going to allow them to wander as far as 500 pixels from their starting point. So they can't go anywhere they want, but they can go pretty far from their home. All right, so now we have these different attributes for this player. Now we're also going to need a way to allow them to kind of move. So here, so to move, that's going to be relatively easy. Essentially to start with this, if they're alive, they can move. So here, if self.alive is true, we don't really need to have the equal true there. We could just say if self.alive, because it will resolve as true anyway. For clarity, I'm going to go ahead and put true there. So if they are alive, then I'm going to allow them to move. Now, how are they going to move? We want to compute the differential in x, or how far they've changed in x, and that's going to essentially be, we've done this a lot of times before, we're going to use trig for this. So we're going to take dx is kind of the left and right, so that's cosine. So math.cosine of their angle, but the angle that we put in is in degrees. It needs to be in radians for math.cosine. So here, math.radians of self.angle. And then we take that, so that's going to give us this number between -1 and 1 for the change in x, how much of their speed is in x. But now we want to multiply that speed, so self.speed times that. And we've done that a lot of times before. And there's our change in x from this speed and that angle. This is how much of it is a change in x. Now, let's also compute that for y, and the only real difference we have here is that this is sine. And there's one other difference we have to make here because of the pygame's coordinate system being backwards. We'll do -1 times that. So since the coordinate system pygame starts with 0, 0 in the top left up here, and it increases going down, the normal Cartesian system kind of goes the other way. And for our purposes, this really doesn't matter, but for it to make sense for us as humans, something that's at 0 degrees will go to the right, something at 90 will go up, because that's what we're used to seeing in school. Where if we didn't invert that, we'd say 90 degrees would go down instead of up. Okay, so now we have the dx computed here. Now there are a couple other things we probably ought to do for this. The thing that comes to mind is we probably want to contain this on the screen and not let them leave the screen. But before we do that, we're going to have to update their position. So self.x plus equal dx, self.y plus equal dy. And now we want to say if self.x. Now we could make them wrap around on the screen, but that's going to be weird with their home position, so I'm just going to contain them. So if self.x ever gets to be less than 0, then I'm going to say self.x equals 0. So in other words, just don't let them go off the left side of the screen. Do the same thing with the other directions. If self.x ever gets to be greater than, now in this case we're going to use screen width. And I suppose I ought to do -1 since the coordinates don't go all the way to that. So if it ever gets to be greater than screen width -1, then self.x equal to screen width -1. All right, so that takes care of bounding it in x. We need to do the same thing in y. And just, I don't know if this is any faster or not, but I'll go ahead and cut and paste this and just change this to y. So if self.y is less than 0, then y equal to 0. If self.y is greater than screen, we need to change this to height. And this to height. Okay, so now we have that contained on the screen. So that's relatively easy right now. We're going to add some things later on so they can kind of change directions and wander around when they get too far from their home position. We'll add that here in just a second. But for right now, we'll just leave this as that. If they're alive, they're allowed to move. and we actually made them move. Now the other thing that we need to add here, we're going to add this self method for render. And for rendering these guys, this is going to be relatively straightforward. The concept here is that we want to render them a different color based on whether they're alive or dead, infected or healed. So I'm going to do that. So I'm going to say if self.alive. So if they're alive, then I'm going to go ahead and draw them as a circle, and I'm going to go ahead and color it blue if they're alive. So here I'll just do pygame.draw.circle. And remember, this takes a surface. We're going to draw to the display surface. The color we said we wanted was blue. So 0, red, green, 255. So there's blue. And then the next thing we need here, and let me pull that list of things back up. The next thing we need is the position, so the x and the y. That's going to be self.x, self.y. Now there is one word of caution, and then the radius. So in this case, I'll just go and make the radius 2 for the normal players, and I want to be solid and filled in, so I'll put a 0 there. Now one word of caution, this x and y, pygame is kind of picky in that it wants those to be integers, so we have to pass those in as integer types. We have to convert it. I don't know why pygame just doesn't do that internally for us, but we're going to convert them to integers when we pass them in. And that's going to allow these to be floating point values or fractional values, decimal point values, as we keep track of them moving and how they're moving. But in our case, when we pass it to the circle, we're going to do that. All right, so it's blue if they're alive. Now, that's the kind of first idea we have there, is if they're alive, but they could be alive and also infected. So we need to take that into account. So we really need to say if self.infected equal true. So inside of that other if statement, we're going to add another if statement that says if they're alive and they're infected, then we're going to want the color to be a different color. So here, let's do else. So if they're infected, we'll do the same kind of thing with a circle. But in this case, let's make the color for infected be, let's do yellow, since that's kind of a warning color, but not a complete warning color. So there we have yellow if they're infected. If they're not infected, then that. Now, if they're not infected, we have two choices as well. We have healed. So I'm going to, if they're healed, that means they're not infected and they're still alive. So I'm going to do if self.healed. And let's actually make this an else if. So we'll do elif self.healed. So if they're healed, let's make them green. We'll just copy that same line. We'll make that green. So now we have yellow is infected, green is healed, blue is not infected at all. And there's one other case here, and that's if they're dead. So that's going to be in the else of the self.alive. And so in this case, I'm just going to draw another circle. In this case, I'll make it red. Okay, and the other thing I'm going to do is to make these stand out a little bit more when they're infected or when they're dead. I'm going to make the radius of this just a little bit larger. I'll make them 3 instead of 2. So they'll be a little, circles will be a little bit larger for that. Okay, so now we have our render. Now, there are a couple things missing in this. One of them is we never did anything with the infection time limit. And so I'm going to add some code to deal with that. And in order to add code to deal with that, I want to add this kind of feature where we can actually have the things become infected. And in order to do that, I'm going to make a method for that. And I'm going to go and call it. Actually, let me put it at the bottom down here. Here, let me put it here. All right, so if this method gets called, they become infected. And the way we're going to keep track of them being infected is the first we're going to do here is the only time we want them to be infected is if they're not already infected. So here, if self.infected is false. So if they're not infected, and there's probably one other thing. We said that if our little people were healed, they cannot be reinfected. So I'm going to also say and self.healed is false. So if they're not already infected and they have not already been healed, then they can become infected. So self.infected equal true. But now that they're infected, we need to start our timer. So what I'm going to do is essentially set my timer. So let's see, what do we call that? Let's scroll up a little bit. Infection timer. And we could do time.time to get that, but what I'm going to do is I'm just going to set it equal to my frame rate times, and I'm going to go ahead and make another constant here that I'm going to call the recovery time. So in other words, this infection timer is in number of frames that they will stay infected, and with about 30 of them per second, if we set the recovery time to 30, or 1 here, 1 times 30, that would be essentially 1 second. If I set the recovery time to 5, that would be 5 seconds. So what I'm going to do is I'm going to go up to the top here. I'm going to add my code for that. So recovery time equal, and let's start that off with a value of, I don't know, let's say they get infected. We'll say 10 seconds. Maybe we'll say a second is like a day. So this is like 10 days that somebody will remain infected. And we could, if we want to model different processes, we could say, well, if the infection period is really more like 14 days, we could change this and make it higher. If it's 21 days, we can make it 21. But by having it up here, we can change it all in that top space rather than having to change it down in the middle of the code. Okay, so now we have our infection timer, but notice we're not doing anything with it. So we need to do something with that. So what I'm going to do is every time we move one of these guys, I'm going to update that. So in other words, if self.infection timer, if that's greater than 0, that means that the person's infected. So what we're going to do is subtract from it. So self.infection timer, we'll just do minus equal 1. So this is going to kind of grow down towards 0 for every frame that we move this little character around. So the little player is going to move around. That'll kind of work its way down towards 0. Now, eventually that's going to get down to 0, and that means the infection time is up. So either at that point they're going to be healed. So I'm going to say if. So if we subtract from that, and it ever gets to be 0, then that means they either get better or at that point they die. So we need to kind of model that. So what I'm going to do to model that is basically say, at this point, if it is 0, then I want to say, let's give them a percentage chance of survival here. So if random.uniform 0 to 1, if that is less than, and let's make this close to the kind of COVID-19 coronavirus that's going on right now. I think the current thing for US is like 3.2%, 3.3%, but we could change this to different numbers. In other countries, it's closer to 5%. Some places it's lower than 3, but let's go and put 0.032. And actually, let's make this a constant. Let's call it death rate. So if that's less than the death rate, and let's go and add that while we're thinking about it. We'll come back and fill in the rest of the code later. So here, death rate equals 0.032. And we could make that higher or lower to simulate different kinds of infectious processes. But in other words, if the random number we got was lower than that, that means they die. And let's actually make it less than. Actually, less than is fine. All right, so this means the person has died. So if that's lower than that, then self.alive becomes false. So they've died. And also, if they're dead, I guess they're no longer infected. Now in the else of this, if it gets to 0, that means now they've survived the illness. So self.alive will remain true, but they're no longer infected. And notice that happens either way, so we could factor that out of the system if we wanted to. But the other part of this is self.healed. That becomes true. All right, so let's go through the logic of that one more time. So if they're infected, they have an active infection, this is going to be, number is going to be greater than 0. If it is greater than 0, we subtract it because they've gone an extra day or an extra time unit into their infection. And once that gets down to 0, they will either have passed away, they'll die, or they'll be completely here. Now, one thing that's a little bit maybe unrealistic about this right now is everybody has the same infection period, and they either die at the end of that or they survive. If we wanted to, we make some randomness to that as well. So in other words, this infection timer, rather than setting it all to the same recovery time, we could set a range, like people will be infected for between 14 days and 25 days or something like that. And that doesn't even necessarily have to be a uniform random number. It could be more of a standard distribution if we want to make this thing more realistic. But we're not worried about this making this more or ultra realistic right now. We're just worried about getting something that works. Okay, now the next part of this that we probably want to do is when we're moving them around on the screen, the way they're moving right now is they're just kind of moving in a direction. We're not using that home position at all to make them change directions if they get outside that. So one of the things that I want to do is I want to make it so that if they get outside of their home a certain distance, in other words, that roam limit of their home, I want them to pick a new direction back towards home in some way. So I'm going to do that down here. So after we've moved them, I'm going to come back here and I'm going to say, I'm going to compute a new dx, and this is going to be the direction toward home, and I'm going to compute the distance from home. So dx here is going to be, let's do self.home x minus self.x. So this is kind of making a triangle from where they are now towards their home position. And then here dy equal self.home y minus self.y. And I guess I don't need the parentheses. I'm not sure why I'm putting parentheses around there. Let's take those off because they're unnecessary. All right, so we have our dx and our dy. So now we want to compute the distance from home. And I suppose I ought to try to use camel case here instead, wherever possible. So let's do distance from home. So distance from home, in order to compute that, I'm just going to use Pythagorean theorem. So there's a square root. So square root of dx squared plus dy squared. So these are the two sides of the triangle. Square those, take the square root of that. That'll give us the hypotenuse, which is distance from home. Now, the angle towards home, we're going to compute that as well. And that's going to be, remember our angles are always in degrees the way we're keeping track of them. So math.a-tan2. A really cool function. We pass in just the two sides of the triangle, dy dx, and it will give us the angle. So that's the angle towards home. So in other words, we have our player. Here's where they are. Here's where their home was. If the distance gets to be too great, if they get outside of the range of their home, we want them to kind of turn around and go back towards home. So in order to get them to go back towards their home at this point, the only time I want to do that is if the distance is too great. So I'm going to say if distance to home is ever greater than, I think we called that the roam limit. Let me just verify that real quick. Self.roam limit, yeah. So if the distance they are, actually that distance from home, not to. So if the distance from home is greater than the roam limit that we set for them, then at this point we want them to turn around. And to turn around, we know the direction to home. We already have that, so I'm just going to say self.angle equal direction to, or angle to home. Angle to home. Okay. So now we've got it so that they're going to head towards their home if they get too far away. And one of the other things that I want to do here, though, is I don't want them to always kind of be going that same direction. So if, in other words, I want them to change direction sometimes just on their own without any reason. So I'm going to add an else in here. I'm going to say if they weren't too far away from home, sometimes they can just change their angle anyway. So self.angle. And here I'll do, let me do this. Let's say plus equal, I don't know, let's do random.uniform. And let's do negative 90, 90. So that's going to allow them to kind of change directions either somewhere in a range of 0 to 90 degrees. So in other words, if they're walking like this, they could start going this way, or they might make a right turn or a left turn. That's going to allow them to change direction. Now, we don't want them to constantly be doing that, though. So I'm going to make this so there's a kind of a probability of that. So I'm going to say if random.rand int, and let's make a random integer between 0 and 30. If that ever comes up to be 0. So in other words, this is, since we're running at, let me say if, not in. So in other words, they're only going to change their angle about once a second, their direction about once a second. Now we could make this smaller or larger, this number, but this is going to essentially be about once a second they'll pick a new direction on their own, even if they have not left the kind of roaming area that we've set for them. If we want to, we could set this angle toward to home. We could give that a little bit of randomness too. But right now we'll just keep it like this. All right, so now we have our kind of person that wanders around. And I think we got most of the parts in there that we wanted to have in there. So before we do anything else, let's go ahead and test this. Let's actually make a bunch of these and then watch them wander around. So we don't have anything that infects others yet, but let's go ahead and just make a list of these and run them around. So up here, I'm going to make a person list. I'm going to start out as empty. And then I'm going to say for I in range. And here, actually, let's do this. Let's do num people. And let's do person list. Append. And we're going to append a person object. All right, so that's adding whatever num people, whatever we set that to. And let's go ahead and make that constant. Let's do 100 for right now. So we're making 100 people in our population. We're filling this list up with 100 people, person objects. Now the next thing we need to do is inside of our main loop, we're going to want to now kind of move all those people around and then have them do something. All right, so to start with here, easiest way to deal with that is I just want to go through all of the people, move all of them, render all of them, and then update the screen. So inside of here, between my clear screen and my pygame.display.update, I'm going to say for person and person list. So for every person object in the person list, we're going to do person.move, person.render. Now we don't have any way to infect people yet. We don't have any way to do anything. But let's see if this gives me 100 people that are all running around on the screen. Okay, and let me move this so we can see it. I don't know if you can see those or not. I might make those little circles a little bit bigger, but there's a bunch of little blue dots. And they're kind of wandering around on the screen. And notice right now we have 100 of them. Nobody's infected. Nobody is. And right now nothing bad is happening. They're just going about their lives, wandering around. If they get too far away, they'll turn around and go back. All right, now let me change the rendering of those so you can see them maybe a little better. So let me come up here. Let's make all these 3, and let's make the dead ones 4 and the infected ones 4. So they're just a little bit bigger. All right, let's see if that's a little easier to see. Okay, I think that might be easier to see on the video. I don't know if you can see those or not. But we got all these little blue people objects wandering around on the screen. And if we wanted, we could make more of them than that. Instead of 100, we could make I don't know, let's make 200 of them. So num people, let's make this 200. Now we've got more of them wandering around. All right, so the next step here is going to be now to add the code that allows them to infect each other. I also want to add a way to pause this and unpause it. So let me go ahead and do that first. So in my code, I'm going to add a variable before the main loop here. And actually, let's start it off as true. And essentially, if it's paused, I just don't move the people. So if paused is true, or actually if paused is, I want them to move when it's not paused. So if paused is false, then we move the person. Now I'm going to add some keys to pause and unpause. So to do that, we'll say if k, let's do p for paused, and let's use u for unpause. All right, and let's run that, make sure that works. All right, so here's the program running. They're paused, they start off paused, I unpause, they move, pause, unpause, pause, unpause. So now I can actually control. That's what I'm going to do is pause them, look at where they are, look at what's going on, and then unpause them later on if I want to. Now, one thing what we haven't tested is that roam limit thing, but we'll get to that later on. But you can tell there, if we just follow one of these, you can kind of tell it'll reach a certain distance and it'll kind of turn around and go back the way that it was coming from. You'll see some of them eventually do that in theory. There's one, let's follow that one. Yeah, so you'll see it hitting kind of the edge of that boundary and then going back towards some center thing. And we have the roam limit set fairly high right now, so they can go quite a ways before they change direction, but they're kind of wandering around doing their thing. All right. Now we're ready to add the kind of infection part of this where they can be infected and can infect each other. And to start that off, let me start off by infecting them with just clicking the mouse. So what I'm going to do first is I want to make it so that I can just click the mouse and choose somebody to be my patient 0, if you want to think of it that way. So in order to do that, I'm just going to say, well, first I'm just going to get them if the mouse button's pressed. So if, or let's do lm left mouse button, middle mouse button, right mouse button equal pygame.mouse.get pressed. So it works a lot like the key press, except it only has 3 buttons instead of a whole mess of them like on the keyboard. And then I'm going to say, in this case, I'm going to say if, and I'm going to go and use the left mouse button. So if L and B, we could put equal true here or not. So I'm just going to say if L and B. So if the left mouse button is pressed, then we're going to get the mouse position. So MX, MY equal pygame.mouse.get position. Okay, so that's actually, we now have the mouse position. And now what I want to do is say, I want to go through every one of the people in my people list, my person list, and say, are they within some distance from that mouse? So here, so for person in person list, so for every person. And now I want to check the distance. So again, the way I'm going to check the distance, I probably should have made a function for this distance, but I'll just write it out again. So if, again, dx, so this is going to be the mouse x minus person.x squared plus, and then here, I'll just copy this. Oops. Change this to y. All right, so that's going to be the distance. So if the distance of that, and I'm going to say if that's less than, so in other words, if the mouse is within 10 units of where if the person is within 10 units of where we click the mouse, they're going to become infected. So person.infect. So we'll just call that method we made earlier. All right, now let's go ahead and see if that works. I believe that should work. All right, so you notice I can click on some people. That's a patient, that's a patient, that's a patient. So I infected a few of those. And now I can unpause that. And now they'll wander around and be infected. Now the other thing is that those should be now have their timer running where they're counting down. So those should eventually either become healed. And actually they went back to blue for some reason. So I need to look at my code for that. But they did go through the timer and eventually go back to a different color, but for some reason they went back to blue instead of being healed. So we'll look at that code. It's either being drawn incorrectly, or here, let's follow one of those. Yeah, so it appears that we're just drawing them incorrectly. So let's go look at the code for what they do when they're healed. Oh yeah, so here, healed, we have the blue for both of those. Healed should have been green. There. All right. Let's run that again, make sure that works. So let me infect that guy, unpause it. Now he'll wander around. Now he's not infecting anyone else right now. We don't have it set up so that he can kind of have this transmission of the sickness, but now he's back to green. And if I infect enough of these, then we should eventually get some that die. But our death rate is relatively low. Somewhere around 1 out of 40 or so wind up dying. But if I infect a group of those, then you'll notice that they'll eventually go through their process and go back to healed. Or if we get unlucky here, we might have one of them that actually dies. All right, so none of them actually have died yet. Let me try infecting a few more here. Let's kind of cluster up here. Okay, so still nobody has died, which is good. Okay, so we're up to the point now where we want them to be able to infect each other. And just to magnify that death so we can actually see some of these die, let's increase our kind of death rate here. Let's go and make this like, here, I'll just comment this out for right now. I'll make it like 0.5, so half of them die. Let's run that really quickly and just take a look at that. So let's infect like these two, those two, those two, and these two. So we should have some of those now. We'll actually die. Let's make sure our death code works. Okay, so notice we had, out of those 6, 3 of them died. So these guys are dead. They turned red. They stopped moving. The ones that are healed continue on with their lives. Okay. All right, so we know that works. And let's put this at, actually, let's put that at 5%. We'll come back and put it at the right value, or something that approximates the actual value for our coronavirus in a second. All right, so now we need them to be able to infect each other. Now, to infect each other, what I'm going to do is I'm going to go and make a little function here that basically goes through all of them and sees and what I'm going to pass to this is going to be the person list. And what it's going to do, or what we're going to do inside here, I suppose we could make that, use that as a global as well, since it's in the main, but let's just use it as a global. So to go through this, what I need to do is, there's a couple ways we can think about going through this. If we think about this list, it's got a whole bunch of people in it, And what we want to do is we want to check every player against every other player. And we're not really going to spend a lot of time optimizing this algorithmically right now. There are ways we could do something more like a distance sorted spanning tree or something like that, where the things that are close together near each other in the tree, and the tree kind of reshapes itself. But we're just going to say, I already have a list. I'm just going to go through the list. So what I'm going to do is I'm going to say for I in range. And the range, how many things are in my list? It's going to be person list people in that list. So we're going to go through every one of those. And for every one of those, we need to go through every other one. So for j in range. And this is a little bit wrong the way I have it. And I need the length of that list. So it's in range length of the list. In other words, how many items are in the list. Suppose we could have used num people there too, but we'll do it that way. But there's one thing about the way we're doing this now, is that we really, where the range starts here, we don't need to go through all of them. We could go to I plus 1 here. So just 1 past that one. And that will get me all the way. And then also that means this list, we could do minus 1. So the idea there is if we have all these, we don't need to go through and check this one with that one, and then this one with this one, and then continue through all of that like that. We basically just need to, in other words, what we're doing is, let's say we have 4 of them. We're going to say start with 1 and go through 3, and then start with 1, start with 2. So we're going to look at this one versus all the ones after it. Then we're going to go to that one versus all the ones after it. Because we don't have to check this one with the one before it because we already did that in the previous step. And then this one with all the ones after that, and so forth. So this is going to do that. And we're doing that with the indices. So now what I need to do in here with those indices is I basically need to say if player list sub I dot infected is false, and player list j dot infected, oops, that's a dot, is false. So if both of those are false, if neither of them are infected, it's totally fine. So we'll just say continue, go to the next one on the list. So if neither of the two are infected, we go ahead and move on to the next item in the list. But if we get to after this, we know one of the two is infected. So what I'm going to do is say if, and really we have it built in, they can only, if they're already infected, they can't be infected. So in this case, if one of the two is infected, we're just going to infect both of them. So we'll say player list I dot infect, and player list j dot infect. So now we've infected both of them. And the only other thing we need to do now is we just need to call that inside of here. So let's say, we'll just do it up here. So check infection. And we made a mistake. Let's see what the problem is. Okay, player list. Oh, I don't know why I put player list. It's person list. I had it right here. And somehow I switched to player, so let's do that. All right, now let's see what we get. Okay, so there they all are. Let's infect one. Oops, that can't be right. All right, so somehow we infected all of them. Let's look at our code again for that. So somehow they're all getting infected. Let me comment that out for a second. Okay, so not entirely sure why they all got infected when I clicked one. Let me run that one more time and take a look again. We never checked the distance. That's why. So one of the things that we need to do is we need to make sure to check the distance between them before we allow them to infect each other. So the only time we want them to infect each other is if the distance between the two, and again, we're going to use that distance check again. If the distance is less than some constant we're going to make. So we need to check the distance between person list I.x minus j.x squared plus, and I'm going to come back to that in a second, so let me just do this. So there's the difference in the x's. So again, that's one side of the triangle. That's our dx, this will be y. There's y. All right, so the way we have this right now is if the distance is below that threshold, then we infect both of those people. Now, we need to define this. So this is how close they have to be before they get infected. So let's add that to our constants. Let's go and make that a radius of 10. So if you get within 10 units of 10 pixels of player, you get infected. All right, let's try that again. All right, so here's the screen. Let's infect that guy. Unpause. And notice that now he's getting near others. When he gets too near to them, he infects the others. Now he's recovered. He can't infect anybody now that he's recovered, but the ones he infected can go on. And notice that infecting that one has killed somebody way up here. And you'll notice that this is kind of now spreading to others around the map. Okay, and that's kind of interesting to watch, because you can see some people recovering, some people dying, some of them who haven't been infected at all yet. But you'll notice this one thing we did right here now is having an effect way over here on the other side of our world. We have killed 1, 2, 3, 4, 5, 6 people by infecting that one. We're starting to get a herd immunity where a lot of people have recovered. All right, so that's where we are right now. Now, before we go on too much further, there are a couple other things I want to do to this code. One of them is I want to make it so we can see how many people have been infected, how many have recovered, how many of them have died. So I'm going to go ahead and make a little printout for that. So to do that, I'm going to need to load a font. So up here, I'm going to do, I'll just say font1 equal pygame.font. And I'm going to use the sysfont function. And the way that works is we specify the name. I'll pick Arial. And we need to have a size. I'll use like a 24-point font. And I'm not going to use any of the other things. So just a basic font in Arial on the screen. And now in my program down here, I want to render that to the screen. So before I do that though, or blit that to the screen, I want to do, I want to make the string I'm going to use. So like let's call it out string equal. So in this case, what I'm going to do is like people. And I could do plus and then str and things like that, but I'm going to use this technique that'll going to allow me to specify like a field width here. So I'm going to say people colon %d or 12d. That means reserve up to 12 spaces for the number of people. Then I'm going to skip some spaces here. So people, and then I'm going to have deaths. %12d. And then I'm going to have, all right, so what else do we want to have displayed here? So we've got the number of people, how many died. We might want to have how many are infected. And actually, let's go and make this instead of number of people, because that's not going to change. That's going to be constant. So make how many are alive. So how many are alive, how many are dead. Let's just shorten this to dead. And then over here, let's make this how many are infected. And then over here, I suppose we also want to know how many are healed. Now, the cool thing about using these percent things in there is I can now put this percent sign here and put a tuple that has all of the things there. So the number alive is going to be the length of the person list minus the number that are dead, or number that are dead. We don't know that number right now. We're going to have to create a variable for that and figure out that out, which we'll do here in just a second. And then let's see, we're also going to now need the number dead. So this is going to be dead count, infected count, and healed. So we need to fill in those variables in order to create that string there. And one of the things, the way that I'm going to go ahead and create that those variables is let me do this. Let's come down here. Let's render this all the way at the end. So I'm going to put that string there instead of up here. And I'm just going to accumulate those inside of this loop. So I'm going through all these people. I'm just going to count out how many of each category there are. So I'm going to go ahead and zero them out here. So dead count equals 0. Healed count equals 0. Infected count equals 0. And now inside of my loop, as I'm moving these, I'm going to say if person dot alive is false, then dead count plus equal 1. If person dot infected equal true, then infected count, let's add 1. And then if person dot, all right, so we have alive, we have infected, we need healed. Healed, true, then healed count plus equal 1. All right, so we've got our list of those there. We have our string now. Now we need to render that. So let's do font1 dot render. And to render that with a font, we need to pass in the string, which we have, which is outstring. We need to pass in whether we want it to be anti-aliased or not. I'll say true. And then I believe we need to pass in the color. So let's just do it in white. So that renders it, and that's going to render it to a surface that we then have to blit. So here, font. We could do it all in one step, but for clarity, I'll make 2 steps here. Font surface. Now we're ready to blit it. So display surface. So onto the display surface, we want to blit the font surface. And I'm going to go ahead and put it all the way in the upper left. So it's at the top of the screen. All right, let's run that, see if that actually works. And there are our counts all at the top. So if I infect one, notice that changes to 1. And now if I unpause this, we should see that 1 go to 2, 6, 8, 9, 10. Notice it's growing now as they go around and infect others. Now we're up to 20, 21, 22. And now notice somebody has died. So we've lost 2 people from our population, but we have 30 some of them that are healed. Okay, so now we're getting close to where we're ready to try to make a lot more people and then see what happens here. So I'm going to go ahead and escape from this right now. And I want to make more people. So I don't want it to just be num people right now is 200. Let's say we want 1,000. And unpause that. And notice that it's moving a little slower now. That's because there's so many people. We have not optimized this yet. But you'll notice that the infection is spreading here. But you notice what started with just 1 is now up to 272. And notice things are bogging down. It's getting slower and slower. That's because as more people are infected, we're having to check more and more distances of them versus other people that are near them. And so that's just taking longer and longer to do. And that's one of the reasons why we said we wanted to have optimization added to this. So what we'll do is I'm going to pause the video for a second. I'll let this run, and then we'll see where it is when we come back. So I'm going to go and pause this just momentarily. We'll let it run for a little bit. Remember, we started that infection over here, and now look how far it spread. And it seems like it's spreading slower than it really is because we're bogging down, because we're having to check all of those. In other words, we're checking 1,000 things against 1,000 other things. And that's a lot of computation, a lot of checking that's going on, which is why the frame rate is bogged down. And that's why we're going to investigate that optimization. So let's go and pause there. We'll be right back in just a second. Okay. Now we are back. And notice that we had 44 deaths, 956 survivors. And we end up with I'm not sure why 988 say they're healed. All right, there may be something with our code there, but the simulation itself works. Now, one of the things we said we want to do is kind of try to speed this up a little bit. So this is the part where we're going to actually talk about how Numba works. So Numba is this kind of module, and let me just quickly go to the web page for that. So Numba, if you go to numba.pydata.org, it's kind of a module, and all we have to do is really install it, which you can use pip to do that. You can actually do that right from inside Python. Import pip._internal, and then do pip._internal.main, and then make in the parentheses for that, make a list. First thing in the list is the string install, comma, second thing in the list, quote, Numba, end quote, end list, end parenthesis, hit enter. It'll install it for you. If you're on Windows, if you have the Python installed in another place, you might get a weird path problem with that. So you can do it from the command line, pip install, pip space install space Numba, and that'll install it that way. And it's actually a really easy module to use. But let's go back to the presentation just for a second, so I can talk about how we're going to go about using this thing. So let's go back to our presentation. And so here's the presentation. And we've written the code. So now we want to make it faster with Numba. And what Numba is, it's a kind of a module that looks at our code for us, and it compiles it into kind of machine code on the machine that we're on. And it allows us to have speeds that are closer to natively compiled languages like C, C++, or Fortran. And one of the things about it, though, is that the code has to be written in such a way that it makes it possible for Numba to do its job. In other words, Numba works best when you have code that deals with like an iterative loop that repeats something over and over, and inside the loop we're doing something numeric inside of there. It doesn't work well when you just give it Python objects or a random Python object and then because it doesn't have the ability to convert that, because Python being a dynamic language, things can change. The type of something can change. You could have a string in a variable and change it to a float, to an integer, to a reference to something. And so Python being this dynamic language makes its job a little bit difficult. But if we write our code in such a way that it fits with how Numba works, we can end up with this tremendous speed increase. One of the other things is, as you dig into Numba a little bit further and look at it, you can actually has features for using both kind of optimized CPU instructions as well as GPU based instructions, and for parallel architecture, vectorizing things. So all of that is kind of built into there. So I'd recommend looking at that, researching it further. But if you're doing something like particle effects in your game, or some sort of physics simulation, fluid flow simulations, things that involve numerical computations on large data sets, Numba can make that stuff a whole lot faster, and really blazingly fast. I would suggest researching that further. There's this numba.pydata.org. But what we're going to do is, before we do that, let's go back to our code and actually look at how we're going to go about doing that. So let me come over here. Let's minimize that for a second. So in our code, in order to do this, the first thing I'm going to do is import Numba. Oops. All right, so you've imported it. And now the way that you're going to go about using this is, there are a number of different features. We're really only going to use this at a very kind of basic level right now. And the basic level that we're going to use this at is, I'm going to change how this kind of function works. The thing that is the slowdown is checking every one of these versus every one of these in this check infection function here. So what I'm going to do is, I'm going to make another version of this function. I'm going to call it check infection Numba. And one of the things, the problem that if I would just tried to turn this into a Numba function, notice we're using Python objects, person list, .infected, person list, .x, .y, and there are some things you can do to make your objects what are called Numba compatible classes, or Numba optimizable classes. But the way we wrote that class, we didn't do that. So what we're going to do is, we're just going to make this one function and optimize this one function to work that way. And it's essentially going to work very similarly to what we did before. But one of the things about that is, we're passing we're using this kind of global list of objects here. And what we really want to do is make it so that it's just operating on numbers in some way. So the way I'm going to do this is, the things I'm going to pass into this this function, are going to look like this. I'm going to put a little comment here to show what we're going to pass in. We're going to pass in a list, but rather than a list of objects like we're using right now, I'm going to make this a list of tuples. And inside the tuple is going to be just the x, the y, and then whether or not that thing is infected. And because that's all we really need in here. We just need to know, have a list of all of them their X position, Y position, and then whether they're infected or not. That's all we need. So I'm just going to put kind of that there. So that's what we're going to pass into this, is this tuple. And when that gets, what that's going to pass back out to us is the list of indices of new ones that need to be infected. So input that looks like that, and then the output of this function, or I'll call it the return value, the indexes that we need to infect. Okay, so in order to do this, we're going to write this function a little bit differently. But it's going to be the same basic idea. So I'm going to copy this. I'm going to paste that down there. We're kind of off by one hair, so. All right, there we go. So this is the same, but now with the list that's coming in here, the first thing I need to do, if I'm going to return that list of indices to be infected, then I need to say I'm going to start off with this empty list inside of here. And then what I'm going to, let's call it this. Let's call it the toInfect list. So that's the ones that need to be infected that aren't. So this is going to work the same way, but I'm going to pass into this list. So here, let's call this the checklist. I'll just CK list. And what I'm going to do here is this is going to be the same, but rather than person list, this is going to be CK list, CK list. This is going to be CK list. So the idea is the same as what we were doing before, but we're going through this list of tuples. And the reason we're making it a list of tuples rather than Python objects is because Numba can very easily optimize that. If it knows the type of that, and the type of that, and the type of that, then it can optimize this into compiling this into something like C language code, and then this process is going to be much, much faster. Whereas if we leave this as objects, it doesn't really know what kind of thing infected is, because it could, in Python, it could change at any time. So we're going to make it so that it's kind of always the same type, and then that's going to allow this thing to compile this code. Now we're going to have to tell it to compile just this function, which we'll do here in just a second as well. So this works the same. Now here, rather than person list subscript I, notice infected is in the 0, 1, 2 position of that. So down in here, we want person list sub I is going to be CK list sub I, but then it's not dot infected anymore. It's offset 2 on that, because again up here, 0, 1, 2, if that's equal to false. And here, where I'm checking that, if that's equal to false and J also 2 is also equal to false, then we're still going to continue like we did before. But now what we're going to do is down here, when we go to check these, we're going to check the distance. And to check the distance, rather than .x, notice the x coordinate is in 0. And these all need to be CK list. So the checklist, this needs to be checklist. That's 0. And the reason we're putting 0 there is this x is in the 0 position of that tuple. CK list 0. So this is now the y, which is going to be CK list I1, because the 1 is in the second position. So CK list 1. And again, the rest of this is all the same. But now we're ready here to return the list of people that get infected. So rather than calling this directly, again, this function doesn't know about these objects, these Python objects, but it can add things to a list. So here we're going to say to infect list dot append. And what we're going to append to that, in this case, is going to be just that index I. And notice this is now a list of integers which is something that Numba deals very nicely with. And we also want to infect J. Now, there's probably one other thing that I want to do here, and that is I don't want I to end up in the list more than one time. So I'm going to say if I is not in to infect list, then we add it to it. And the same thing for J, not in. So if I is not in the list, then we add it to the list. And we'll do the same thing with J. So down here, if J is not in to infect list, we add it. So in other words, we only add them to that list. And now after we're done with all these for loops, we're just going to return that. So we returned both of those things, or a list of all of the items. So now in my main, I just need to change how I use it. So before I was calling this check infection function. But now what I need to do is I need to make that list of tuples. So for person in person list. And now I'm going to let's make my list to pass to my new function here. So let's say let's call it plist right now. So, and to make it more clear, let's say plist tuples. So plist.append, plist tuples.append. Now, the kind of tuple we want to add is going to be person.x, person.y, and then person.infected. Now, one thing about this again, because this is we want this to be something Numba can deal with, I want to convert these into some kind of form that is always the same, so we don't rely on Python to sometimes have a float, sometimes have another value. So we're going to go ahead and do pass those in as a float, like I have right there. So in other words, when we're calling this function, I'm going to make sure all of those things have some known type. And in this case, I'm just going to make that a float. And that's going to make Numba's job easier because it can optimize that. It can say, hey, when the function's getting called here, you're always passing in floats. So I can always assume it's going to be a float, and then it can calculate that using that. Now, the person.infected is always a Boolean, so I don't really need to cast that as anything. But these two, I'm going to pass them as like that. Now that I have that list ready, we're going to go and call the function. So to call the function, we called that check infection Numba. I believe that's what we called that. Let's just scroll up. Let's just scroll up for a second and look at that. Check infection Numba. We're passing in the list that we just created, which is plist tuples. And that's going to return to us all of the ones that now need to be marked as infected. So here, I'm going to go and say for, or actually, we don't need to do that. We just need to do for I in range length of, actually, we need to, let me divide this up into two steps. I could do the length of this thing right here, but let me do it. To infect is that. And let's just go through these rather than arrange. Let's do to infect. So it's going to go through each one of those one at a time. And now I just need to say person list sub I dot infect. All right, so now this looks like more work than what we were doing before. Before we just made this one function call. And now we're kind of preparing this list and then pulling the things back out of that when it's done. But as we will see, this should be much faster, assuming that everything works okay. And apparently we have a problem. Let me look. Oh, typo. Tuples. Tuples. All right, let's try again. And we still have a problem. CK. Oh, somehow that just got CK instead of CK list. All right. And now it's paused. Let's unpause it. And you'll notice that they're actually faster now than they were before. So even though there are 1,000 of them, much faster than they were using or actually, this is the same speed. And that's because we have not told the Numba to do anything with this. Now, how do we get Numba to now do something with this function? That actually turns out Numba, once you have your code set up the right way, is really easy to use. And the way that I'm going to show you to use this is the way Nimba works is it uses what's called function or method decorators. And essentially what that does is that allows you to associate extra code that gets run on a function or on some sort of object. And the way we specify that we want to use a decorator is with this @ sign. So what I'm going to say is @numba.jit. And really, that's all I need to do. So that @numba.jit that I added there is basically saying use the function decorator numba.jit. And jit is just in time compiling. And by not putting anything inside of the parentheses here, it's going to automatically now convert this into kind of using its most aggressive method possible. You can actually pass things into this to control it a little bit. But let's go and run that and see. Now we should see that thing. All right, there it is running. Let's unpause it. And now notice it's much faster than it was previously. And depending on the nature of your code, we have a problem. So it's infecting the wrong thing. So we'll look at that here in a second. So it's got to be something with how we've created the return list. All right, so let's actually fix this. And let me change this code around a little bit here. So we're pending I, we're pending J, we're returning the I and the J. And then down in our main, that seems okay there. So let me think about this a second. All right, so we're adding everybody in here, and then we're calling the function. We're capturing what comes back from the function. That seems okay, so it's got to be up in our code up here. So let's take a look at this again. Oh, I see the problem. We have 0, 0, we have 1, we forgot to change that to a 1. So everything, the idea was right, we just had a cut and paste error where we did not change something. Okay, so here we go. We'll infect that one person there, unpause it. And now we have it running fast and going through. and all of those quickly infecting everybody else. Let's move that where we can see the whole thing. So watch how quickly this is now going to ripple through the entire population. And then we'll make one final change to this code here before we're done. But you'll notice that I already have some deaths. Some people are healing. There's still a few people who have not been infected. I think there's one left who has not been infected there. But notice that as more people heal, he's going to get less and less likely to get infected because everybody else is going to heal. So we have now 51 dead, 8, 6, 4, 3, 2, 1. Nobody else infected. And we've got one person who kind of escaped unscathed here wandering around. That's totally has never been exposed, but now never will be because of the herd immunity, that everybody else is immune. So it's very unlikely to get that. Now, this was with a very high kind of travel distance. So notice how quickly that spread through the entire population. But before I do that, there's one other change I want to make to this code. I want to make this a little more realistic as far as the numbers. So we're going to use these individual people as stand-ins for a group of population. So what I want to do is I want to put in the population of like a large city in here. So let's take New York City, since that's been in the news recently. And I'm going to call this, instead of num people, I'm going to call this population. And I'm going to set that equal, if I Google New York City's population, it's like 8.623 million. All right, so let's set the right number of zeros. 8.623 million. Now, in order to display that on the screen, though, that's an approximation for the population of New York City. What I want to do is come up with like what's the actual population per dot? So I'm going to come up with a factor for that. So pop per dot. So we're using this as kind of a stand-in, a rough stand-in. So one person is going to equal a block of people here. And so that's going to be the actual population of our city divided by the number of dots, so num people. And now what I'm going to do is I'm going to take this population per dot thing, and I'm going to, when I go to print these out on the screen, I'm going to print that instead, so we can actually see how many actual, as a stand-in, how many people would have died. So to do that, all I really need to do is take this whole thing down here, and let's just do this. Oops. And multiply that times the population per dot. And I'm going to do that on these other, all the other ones as well. So these are going to give us much bigger numbers, but it's going to give us something more kind of, I wouldn't say realistic, because this is not a realistic simulation at all. But it's going to give us something that can act as a stand-in for all of these. All right, so there we are. Let's infect one. You'll notice that that equivalent to 8,000 people being infected. Now we unpause this. And let's see that. So if this is New York City and everybody's running around doing whatever they want to, you'll notice that the number of infected is just growing exponentially. And then let's let this play all the way out. And then we'll try this kind of with social distancing here in just a second. We'll see what happens. And so we'll let this run until everybody is either dead or healed. And I notice we still have a few people who've not been infected. This one's exceptionally lucky. We're just kind of running the gauntlet there. And he might actually escape unharmed. We've got a few infected left. Okay, now no more infected. And notice we had 319,000 deaths that happened in that just in New York City alone. And this is what happens if you just the whole population ends up getting infected here. And now let's try this with that social distancing concept added in Xenom. Notice there's still a guy here that never got infected, but he's okay now. He never will be because the rest of the population cannot get it and cannot give it to him. All right, now let's add some, as the final thing we'll do in this example, is let's go back up and make one change to this. And the change we're going to make is the roam limit. So we let people go really wide here, and it spread like wildfire. People died like crazy. So let's lower this down and say, let's not allow people to go more than 15 units away from their home. And let's see what happens. All right, so here's the thing. Notice it's the same kind of thing we had before. But let's pick a person somewhere. We'll just kind of randomly pick one. And rather than pick one that's off by himself like that one, let's pick one that's kind of in a cluster of other ones. So let's pick that guy there. Let's it doesn't look like the roam limit is working correctly. So something is wrong. Let me go back and look at that. Roam limit 15. Let's check that code. I don't know if we ever checked that earlier. All right, so looking at that, distance from home. If the distance from home is greater than the roam limit, that looks okay. I'm not sure why that's not working. Look at that one more time. No, they're still not going the right way. Here, let me infect. So maybe I have that backwards. Let me go back and look at that one more time. And let me pause this because I have a dog barking that needs to come in. So hold on one second. Okay, the dog is outside now. He might still bark, but he's outside. But I found the problem in the code. Notice this is supposed to be a square root. That's 0.05 there. So we just need to change that. And now we are ready to run this again. Now we have our social distancing working. So I'll infect one player or one person. I'll unpause. And now you'll notice that they aren't moving as far as they did before. They're kind of just staying around their home. And so this guy here is not really infecting anyone else right now. Now it's possible that he could get unlucky and get just far enough to infect probably that guy. So he finally got another one. But notice how long it took. And now he's actually better. And this guy is going to have to get lucky to infect one of the ones near him. And so at this point, you'll notice that we infected the same amount when we started, but because they're not traveling very far, they have both gotten better, and all of these people are safe. So we've now had nobody die. And, well, I guess in this case, this is representing 17,000 people got that because they weren't running around infecting everybody else. It didn't spread very far. So on the fly, we could, here's a little pocket of people here. Let's infect somebody there. You notice it will spread a little ways. But with just them staying away from other people, we end up with this two things. Notice it's not blowing up like it was before. It's not rapidly expanding through the whole population or running through it like wildfire before. And you also notice that because they're staying away from each other, the people that are sick are getting better, which is infecting fewer other people. And that will still spread around a little bit like we see going on up there. But chances are that this is going to spread very, very slowly, if at all, and not through the entire population. And for those of you staying at home who wonder why we're doing the social distancing, this is kind of what we're dealing with. The other advantage of social distancing, which I think hasn't been talked about enough, is it's also, notice that this is, you may have heard the term flattening the curve used when talking about that. And one of the things we're doing here is notice that even though we still have people infected, it's been a much slower process, which is allowing the medical establishment time to deal with people, make sure they survive rather than being overwhelmed. The second part of that a lot of people don't think about is this is also buying time for scientists to come up with treatment plans that work, buying time to come up with various forms of plasma therapy to use and do trials and make sure that the way that they're going about treating it actually works. And notice now, even though we have infected more people than we did in the first example, because everybody's staying home, everybody's okay now. None of these people are going to get it. Let's do one more group of people. Let's pick a place. Here's a pocket of people down here. Let me find a cluster. Here, let me pause it and find a place where people are kind of bunched up together. Looks like probably right here. So let's pick one person in there. Okay, well, we got 3. And let's go ahead and unpause that and watch that progress there. So notice it's very slow progression rather than fast progression. And the people that aren't, it's not like they're not coming into contact with others, or they're just not coming into contact with as many because they're not roaming around like they were before. They're staying near their home, only doing things right around where they live. And so it still spreads once somebody has it in the area, but not like it did before. All right, and to contrast that again, now that we made that other change, let's just change that one variable back. Let's change this from 15 to, let's say, well, rather than people staying home, let's say they just go around their neighborhood. Let's change this to be, let's make it like 50. So that's not quite as big as 500. It's only, let's make it just 3 times what it was. Let's make that 45. Let's see how that makes a difference. And I actually don't know. I have not run this before at this, but let's try it. Let's run that. It's paused. Let's pick a cluster of people. Where's a good cluster of people? Here's some up here. Unpause. And you'll notice that even with people traveling like just three times the distance, still not really far, you're going to see this thing start to spread much more quickly. So notice the way the population is ballooning relative to the previous example where their limit was 15. This is still going to have a better outcome than before where we've had 500. But you'll notice that it's because it's moving more slowly through the population, but it's still getting there. Eventually, even though the infection started here, it'll eventually probably make it over to here. It'll just take it a while. And we already have 51,000 dead people. Remember that last example we did where people stayed home? We had people that got infected, but we had no deaths from that. And that's the difference that running around your neighborhood and interacting with people versus truly staying home and staying away from people can have. You notice this is still, it's going through. The curve is flattened some, but we're having still a lot of infections. It's just taking a lot longer to get through them. And to contrast that one more time, change this back to 15. Pick a person, unpause. We're giving that person more time to heal without infecting other people, and it is growing a little bit, but you'll see it'll be localized and it'll be a much slower process here. People should start healing any minute here. Oh, there's somebody who's healed. And this, as I said earlier, this is not an accurate model. It's not intended to be. There are ways to more accurately model these things using differential equations rather than a graphical simulation like we're doing here. One of the other things to note is the population density makes it worse. So the closer people live together, the more likely they are to come in contact with one another. So again, if we added more people to this thing and had them more densely packed, they'll have to stay even more isolated than in other areas. And if I have fewer people, they're less likely to interact. So, and that's why you see pockets of this in New Orleans and New York City, things like that. So in other words, this is why you should stay home. So let's go back to our presentation for one last thing here. Okay, so finishing up here, one of the things that you might remember that I said was that this Numba thing has a lot of other features that we're not using right now to make things faster, GPU resources, CPU instructions, and it can really make certain kinds of code like hundreds or even thousands of times faster than if you run it just in Python. All right, so that's all for today. Stay safe, stay home, and work on your projects. I believe next week what we're going to do is we'll have a day off, and I'll give you time to work on your lab projects, but I am going to post a thing so you can actually perform an update. Give me an update on how your project is coming along. All right, that's it.